So let's take a very simple example using the remaining time that we have, which is that of a rectangular waveguide. In the past, we have only been doing theory. And let's take this as an example. Let me see if I can get rid of this. Okay, you get rid of that. And then we can take the key TE case first for the rectangular waveguide. And of course, this one EZ equal to 0, HZ is not equal to 0. Sorry, it should be the other way around for the TE case. And then the boundary condition that my size of H. So for TE case, I look at size of H, and it should be expressible in terms of size of HS, XY, with a dependence of a propagating wave. Okay, and if that is the case, then the reduced wave equation that this satisfies is equal to that. Okay, is equal to that size of HS, x of y equal to 0, with the boundary condition that on the waveguide wall, okay, this boundary condition should be satisfied. Well, you can write the solution for this equation quite readily because the transverse Laplacian would be just equal to that. Okay, and you can use the separation of variables and show that psi HS XY has to be something like A cosine of beta XX cosine of beta YY. Okay, you can also choose sine as well, but we have chosen the cosine so that on the waveguide wall, at least on the one of the two walls, like the x equal to 0 wall, which is this wall over here, and the y equal to 0 wall is this wall over here, and this would satisfy the Neumann boundary condition on the two walls. And then in addition to satisfying the Neumann boundary condition on this wall and that wall, you will have to take its normal derivative, and that you know how to do, which means that if you're on this wall, what is the normal derivative? What direction should you differentiate this function to find the normal derivative of the scalar potential or the pilot potential on the waveguide wall? Anybody on this wall, what is the normal derivative? And what derivative should I use to get the normal derivative on this waveguide wall? Or also on this waveguide wall, the two walls are parallel to each other. The two normals are also the same. So the normal derivative on this waveguide wall is the same as the normal derivative on that wall. And what should I do in order to get the normal derivative? Anybody? What about Zheng Liu? What do you think that normal derivative should be?
So I was not quite catching.
Okay.
Can you repeat the problem?
Yeah, I want to ask you. You have to impose this normal Neumann boundary condition on the waveguide wall. So the normal derivative from this wall and that wall would be differentiating in the normal directions, and that would be differentiating with respect to x. And then you have to impose the fact that the normal derivatives have to be equal to 0 on the top and the bottom wall, and then those two walls you have to differentiate with respect to y. Okay, you differentiate with respect to x, this becomes a sine. You differentiate with respect to y, this becomes a sine. You impose the boundary condition to be 0, then you will find that, in fact, beta x has to be n pi over a, and then beta y has to be n pi over b. Okay? And those are the beta X and beta Y that you have found. But then the dispersion relationship has to be satisfied inside the waveguide wall, because these are solutions to the Helmholtz wave equation. Okay, beta Z squared must be equal to beta S squared, which is omega squared mu epsilon. Okay, you can show that this to be true, and hence beta Z has to be equal to omega squared mu epsilon minus beta X squared minus beta Y squared. And if you plug in the value of beta X, this would be n pi over A squared minus n pi over B squared. Okay, you'll find that if the frequency is too low, and if you pick a certain m's, okay, this number becomes imaginary. When this number becomes imaginary, it says that you do not have a propagating mode anymore in the z direction, okay? And you will have evanescence wave. If omega squared is less than a certain frequency, and that frequency is determined by the second term called the cutoff frequency, and it depends on m and n. Okay, so each of the mode, if you choose a certain m's and if you choose a certain n's, then you're actually picking a special mode of the waveguide. And that particular mode has a cutoff frequency when omega is less than that value over there. Okay, so you can go and read the lecture notes for TE mode. 2E10 mode has lowest cutoff. And it's the mode that is most important. It's usually called the dominant mode. Okay, this is called the dominant mode. Okay, I'll stop here since I'm running out of time. Are there any questions?